Okay, it sounds like got a bit of a full house here, so thank you to everyone for joining. My name is Josh Boland. I lead the East Coast of the North America for Cast AI. Also have with me Phil Andrews, our field CTO. I'm going to be walking through a quick presentation before we get into the demonstration, talk a little bit about the differences from what some of you are using today as part of the product and the way that we intend the product to be used in its fullest form. So Cast AI is at its core an automation platform. Right? While we do certainly provide reporting, which some of you are using today free of charge, we are at its core, again, an automation platform that's focused on optimizing performance and cost of Kubernetes in the cloud. We are releasing other types of platforms for the cloud, including database and AI and security products as well. But for the time being, we're just going to talk about, again, optimizing Kubernetes in the cloud for performance and for cost. So the dirty little secret, I think most of you probably are all aware of, it wouldn't be on this webinar, is that far less of what we're provisioned is actually in use. And in fact, our studies and studies that have been run by other analysts show us about 13 to 15% of Kubernetes that's been provisioned is actually in use at any given time. That's a staggering amount of waste and something that you probably would see a lot of raised eyebrows at any other area of the business. But because Kubernetes is actually a very complicated platform to work with, we accept that. On the far right is what Cast AI is doing. Our automated optimization allows you to really consume everything that you're provisioning. And make sure that you're not experiencing all of this waste. So I find that a picture is worth 1,000 words, but ultimately what we're looking to do is provide you what we don't believe any human could accomplish with open source tools or reporting or other types of things, and really taking the most, getting the most out of Kubernetes infrastructure, which was intended to scale up and scale down based on your usage. So for some of you on the call today, you're using 1/3 of the platform, and that is our reporting. And we do provide that free of charge. Provide you cost breakdowns on a per workload basis, and pivotal view of every important metric across all Kubernetes, all workloads, and across all cloud providers. But the secret sauce to Cast AI is really our AI-driven automation that is leveraging machine learning algorithms, constantly simulating scenarios every 15 seconds, looking for nodes to decommission, workloads to optimize, instances to right size, and more importantly, to right type, and then we're executing those changes. And the reason we can do so safely is the AI is not only obsessed with performance and cost, but also with best practices. And we do provide you, the human, with guardrail overrides for any particular risky outliers that you may encounter. And what we'll find is there are two types of individuals who come and make an investment in Cast AI. The first is someone who has discretionary budget, in which case they can spend less on Kubernetes infrastructure waste and more on additional DevOps engineers or particular productivity tools that can help the organization build and grow. We also have other stakeholders, typically our DevOps personas, who have been given targets to lower infrastructure costs, to lower cloud costs, and they find that it's either very painful, i.e. toil, or it's next to impossible because of a lack of control. So for political or technological or sheer scalability reasons, they find that they can't hit those targets. And so we do find folks buying Cast for different reasons. We find folks that look at Cast for just to free up engineering resources to get them back on work on more strategic projects. We do find those folks who are just looking to save costs. But we're putting up here a couple of different customer case studies you can find on our website, from Nielsen IQ to Akamai and 24/7 Games. So again, other vendors in the space, generally speaking, are providing you with a report and recommendations on where your waste is, which is certainly helpful. We are an automation platform that's actually going to execute on those recommendations and do that in real time. So with that, I'm going to introduce Phil and walk you through the platform.
Thanks, Josh. Go ahead and share my screen out here. Well, I want to start by just kind of giving a glimpse of what life after Cast AI looks like, and then we'll kind of go back and talk about how Cast AI can actually kind of bring that to the front. So what we're looking at here is relatively large cluster. This happens to be very heavily spot utilization. We have some customers that run fully on demand, some that run fully spot. Most of them are a mixture, right? There's some workloads that can run on Spot, more microservice oriented, newer stuff, or potentially development versus production. But then there's a lot of other things that might have been lifted and shifted that are more legacy code that still need to run on demand. So either way, there's still usually quite a bit of savings within the Kubernetes environment. So when we look here, you can see we've got a few different instance types here, right? We've got T2 standard 60s, we've got N1 customs, and this happens to be a GKE cluster. As Josh was mentioning, we work on GKE, EKS, and AKS. We've got a few different shapes here. If we're looking at the pricing on these T2D standards are 0.6 cents per CPU hour, very inexpensive, and they're a pretty solid performance machine. But if you can't get enough of them, if there are not enough available on the spot market, we have to go try for other types. For instance, these C2D high CPUs, 0.9 cents per CPU hour. A little bit more expensive, but still a lot cheaper than on demand. So this is Cast AI looking through all of the market for this particular cluster. And every time they need capacity, we're picking the most cost-effective shape and size that's also available in the spot marketplace. Now, when you're working with on-demand, you don't have to worry about what's available, right? Because generally on-demand instance types are always available. Some of the busier regions, that's not always the case, but generally speaking, they're always available. So in that case, it's going to be looking across all the instance types and finding the best shape, size, and price of on-demand instance. We look at the CPU resources here. These are 100% allocated. When we say allocated, that's CPU requests of the actual applications compared to resources, allocatable resources on the nodes. So these 60 core nodes are completely full. If we look at memory is not quite as full. And that's okay. Memory is about 1/10 of the cost of CPU. So the goal is to prioritize CPU as our first optimization vector and memory as a secondary. Get CPU tight first, and then get as close as you can on the memory side of things. And that's where we can get the best cost savings. So if we look at this whole cluster, this is a customer that's been with us for 2 years now. They're running 95.2% requested to provisioned. This is incredibly, incredibly high. The industry standard is about 56% requested to provision. Everything between 56 and 95 is wasted dollars, wasted money. The graph that Josh had showed earlier between the yellow and the blue line, that's all waste, right? That's completely unused compute resources. We look at our graph down here. A lot of the questions that we get are, can you scale fast enough? I have spiky workloads. This cluster scales from around 6,000, 5,000 CPUs at night to north of 20,000 CPUs, sometimes close to 25,000 CPUs during the day. That's a very large and very fast scaling curve with no issues as far as scaling velocity. One last thing I want to talk about on this page is this customer does use a few GKE nodes. They actually get pre-release access to GKE nodes, new instance types before they're released. They're running those using the GKE cluster autoscaler. There's 32.5% waste on those nodes. Now, the customer doesn't really care because those nodes are free. They're provided free for testing purposes. But that's a lot of waste. If we look at the Cast AI nodes, 3.8% waste. There's only 3.8% over provisioning on those Cast AI nodes. Now, this is a very sophisticated DevOps team. I mean, they're, I would say, world class. Not everybody's going to have the technology and the ability to get to these types of numbers, but generally speaking, we see between 85 and 95% requested to provision ratio among our customer base. That's being able to effectively use just-in-time capacity in the cloud and in Kubernetes. That's what Kubernetes was designed for, is to make sure that you have the capacity when you need it, you have the scale when you need it, you can quickly respond to capacity increases and decreases without all the extra waste that previous VM life cycles brought with it. When you're trying to bin pack multiple applications on a VM, you'd end up with a lot of noisy neighbor issues and a lot of problems. Correctly sized and designed Kubernetes infrastructure, you can run at these levels of allocation without any performance issues. It's all about making sure that your environment is tuned and using an autoscaler that's going to be aware of what your needs for your application are. I'm going to go back in to see how we actually get there. So first, I'm going to show how easy it is to actually connect a cluster. I know some of the folks on the call have connected clusters, at least to the read-only phase in the past, But for those who haven't, I have an EKS cluster. So first stage is just a quick deployment. So it's going to be a kubectl apply for a YAML file. That YAML file is going to create our namespace, and then it's going to create our deployment under that namespace. This piece is entirely read-only. It has zero ability to actually change anything in the cluster. If we actually take a look at the cluster role, it's got only get list and watch verbs. So this first piece is just doing things like kubectl get pods, kget nodes, kdescribe nodes, things like that. It's collecting up a map of the cluster so that we can analyze it and look for savings opportunities. I'm going to go ahead and run this. You can see here we're deploying our namespace, and then we're deploying the rest of our service. That's it. That's all it is to get into phase one. Very little. There's no AWS or GCP credentials needed, nothing. That first step is just running that YAML deploy, and now we're connected. So that's in connecting state. Typically, we get our first report within about 45 to 60 seconds, and that's going to give you an instantaneous snapshot of where the cluster is at today, right this second. And then over time, it's going to give you a metric of where you could be as the cluster kind of cycles up and down throughout your business day. So we'll let that kind of think for a minute. It's about a minute. There we go. It's already ready. So with this cluster, what this is telling us is today, it's costing us about $490 a month. If we optimized it, just sticking with on-demand, getting rid of waste, choosing better instance types, leaving everything on the same on-demand instance types that they are today, we can get down to $279.23. That's about a 43% savings with just picking the most correct instance types and sizing the cluster appropriately. Now, everything on this page, as we said, we don't have any read-write permissions. So everything on this page is read-only. Everything on this page is simulation. So you can see what some different opportunities look like. For instance, if you wanted to run some of the workloads on Spot, now we're talking 83% savings. If this is a dev environment where you're willing to take a little bit more risk, great. You could get 83% savings by moving some of it over to Spot instances. If you're using microservices and all the way up through your prod stack, they're all stateless and they're very resilient, you could use Spot all the way up through prod and get these savings in all of your environments. There's a few other options here. You can see what Graviton would do for you. Graviton's typically 6 to 10% additional savings. In this case, it's about 6.3%. And lastly, you can see what shutting off your cluster during off hours would look like. This is a tremendous savings on those lower environments. If you've got dev clusters, if you got performance clusters that are only used for performance testing once every release cycle, being able to hibernate the cluster, spin it down to a minimum capacity, letting it sit there idle, and then spin it back up when you need it, has tremendous savings on those lower environments. So if we look at this is simulating if you were at 15 hours a day, 5 days a week. So this would be covering, say, US East and US West development times, shutting down at night and then shutting down at the weekends. That's another 55.4% savings. Right there. If you've been tasked with cutting 20 or 30% off of your budget, just by hibernating your lower environments, you could achieve 55% on those lower environments. That might get you there, right? If 50% of your spend is dev, just by shutting down and hibernating those lower environments is going to get you close. And if we also do the other right sizing, it's going to get us there. Okay, now we're going to go back and talk about what actually Cast AI is going to be doing for the enablement. So this is my demo cluster. So this cluster is made to simulate those industry standards that we talked about. About 56 to 60% is the actual requested to provisioned. It's about what we've got laid out here in the low 60s. This is what most customer environments look like when they first onboard to Cast AI. Typically, the CPU to memory ratio isn't real well defined. Some nodes might be better than others. For instance, this node is not bad from a CPU to memory perspective, but some of these other ones are much more CPU heavy than memory. This is very typical of a lot of the clusters that we encounter, where somebody, it might have been 2 years ago, 3 years ago, decided to use a specific instance type and stuck with that ever since then. So your whole cluster is some accumulation of M5s or maybe C5s. It ends up creating this poorly fit, especially as you add more applications, you add more tools, you add more Kubernetes resources. Maybe you've added some stateful sets alongside of your more stateless stuff. You've lifted and shifted some of your legacy applications. All of those items create more disparity in the cluster where your scaling curve is not going to properly match what your instance type is. Like these applications are not fit well for an M5 large. Some of them are better fit than others, but by and large, this is not a great fit of an application on this. This is largely constrained by the rules of cluster autoscaler, right? When you've got a typical EKS, GK, or AKS cluster, you have to set up node groups, you set up node pools in GCP and Azure. You define which instance types you want, and you can have a cascade. You could have 3 or 4 different node pools that cascade through different instance types with a goal of trying to be better. What we found is the more node pools and node groups you create to try to be better fit, the further away you get. Because every time you're creating a new node group with a different size instance type and trying to get things to fit better, you're actually creating more segmentation in the cluster, which is creating more opportunities for waste. The correct way to approach this is actually deciding the instance type at runtime, not deciding it in a static node group. Node groups really don't have a reason to exist anymore in Kubernetes, other than the fact that everybody still uses them because they have used them for a long time. Right. Node groups were originally designed as a way to segregate workloads, a way to, spin up different instance types for different workloads. That was great 3 or 4 years ago. Today, Kubernetes has all the features built into it that you don't need that. You can segregate workloads using things like pod anti-affinity and node selectors. You can also do things like topology spread constraints to spread your workloads out, or use pod disruption budgets to increase your resiliency. All of those things didn't exist several versions ago. They do now. That's how you can prevent noisy neighbor. You can prevent other issues by making sure you're using correct Kubernetes configurations that are available today. That means you don't need to use node groups anymore, which is great because Cast AI doesn't use node groups. We create whatever the proper instance type is when you need capacity, and we add it to the cluster. So we'll go through and I'll start turning on some settings here. So we're going to turn on our unscheduled pods policy, and we're going to say this is a dev cluster. We're going to just use some spot instances. Now, we also have the option to use spot fallback. A lot of people are afraid of, in people's mind, the de facto scare is Black Friday, right? Everybody is impacted by Black Friday in some way, shape, or form. Whether you're an ad tech, a martech, a retailer, somewhat finance, you got more transactions coming through. Nearly every industry is somehow impacted by Black Friday and Cyber Monday. So everybody has that fear hanging over them when they're trying to figure out what they're going to do for their capacity management. When we talk about spot instances, people think there's not going to be any spot capacity available on Black Friday. And then what happens? I'm not going to get the instance types. I'm not going to get the capacity I need, and I'm not going to be able to scale my service properly. As a result, people stay on demand out of that fear. The kind of more proper way to do it, more forward-thinking way to do it, is use a tool that can handle those cases where there may not be spot capacity. We actually find that Black Friday isn't that bad. We don't get as much interrupts. We don't get as much out of capacity errors on Black Friday. It's actually about a week before that we see a lot of issues with spot capacity. That's because a week beforehand, everybody is panicking and moving their workloads back to on demand, which is sucking down that spot capacity. It's pulling down that reserve. During Black Friday, we have customers using Cast AI that almost never fall back to on demand at all. They stay on spot all through Black Friday, all through Cyber Monday. And that's because we're constantly arbitraging across all the different instance types that are going to be a good fit, and we're able to find them different resources. Now, on the off chance there isn't any capacity, we have spot fallback. And the goal there is if they can't get you a spot instance, we're going to automatically swap back to on demand. It'll look just like a spot instance to your workloads, but it's going to be an on-demand instance. Now, you can set a timer that's going to try to move you back to on-demand. One of the biggest issues with trying to do this with Cluster Autoscaler and the default settings that are available, you can't move back. You can fail back to or to on-demand. However, once you're there, you're stuck there. You have to manually go in and remove those instances and move yourself back to spot. With Cast AI, we can float back and forth between spot and on demand, depending on what the market conditions look like. You can also set this to be whatever time frame you want. If 30 minutes is too aggressive, if your applications have a long startup time, maybe you set it for a couple hours, for 6 hours, whatever the case is. Obviously, the longer you set it for, the higher the cost, but it's going to be kind of trade-offs. We also have interruption prediction. One of the big issues is you only get 2 minutes on AWS, 30 seconds on GCP, and 30 seconds on Azure when an instance gets interrupted. Now, today, we can actually monitor for interruptions and predict when they're going to happen and start migrating you off those high-risk instance types before they actually get interrupted. Lastly, diversity of spot instances. The worst thing you can do is have 60, 70% of your cluster be all, say, C7A 4XLs. Now, if C7A 4XLs have a drought in capacity, you could lose half or more of your cluster in one big interruption. Allowing for spot diversity, this is going to allow you to spread your instance types out across a cost threshold. Now you're going to be spread across multiple families, multiple sizes. It's going to make it so that an interruption is not going to hit you nearly as hard. Obviously, we do support x86 and ARM. I only have x86 workloads here. Lastly, the constraints. So constraints are able to be dialed in based on the cluster, based on the needs. Some, for instance, on GCP, some of our users don't like E2s because they get unpredictable performance. E2s will give you kind of whatever CPU is available. Some of them are okay. Some of them are pretty old and don't work real well. So a lot of times people exclude those entirely from their plan. Other times it's you need a specific type like storage optimized. Maybe you want to include or exclude specific families. We've run into cases where people can't use any AMD family because it interacts poorly with their applications. This allows you to kind of dial in all those settings to make sure that you're getting instances that are going to work for your application. We do recommend people keep this as broad as possible because the more you narrow it down, the fewer choices the autoscaler has, and the more it's going to be more like a static cluster autoscaler. You want to keep your options open, but make sure that if you have any instances you need to rule out for technical purposes, or if you need, for instance, like GPUs, you can dial those in based on what you actually need. So for mine, I'm going to leave it pretty much wide open here. One of the things that we do see, which is kind of cool about this, if you're using spot instances and you leave the choices pretty open, you'll see amazing arbitrage between the different instance types. Last year, GCP launched the C3 instance family. It was their latest generation, 4th gen Intel Xeons, very high-end processors. When they first launched them in March, they cost 0.4 cents per CPU hour. We looked at some of those other instances earlier. The cheapest was 0.6. So you're talking a 33% discount over the cheapest other choice that was out there on the market. 0.4 cents is the cheapest spot price anywhere in the world. Cast AI automatically rotated those into the customer's cluster on that first month. By the end of that month, they were saving $250,000 across their entire fleet of instances. That lasted 6 months. That company saved $1.5 million in just a massive windfall on their cloud spend. And it was entirely due to arbitraging different spot instances through their infrastructure. The cost increased 4x in August. We automatically migrated those expensive instances back out of the cluster and got them back to their normal baseline. But for that 6 months, they saved $1.5 million without doing anything. It was completely automated behind the scenes. We'll go ahead and save here. So we're going to talk about bin packing. So we're going to enable our node deletion policy. Node deletion policy is just our downscaler, right? It's just going to be how we delete instances. So the node TTL is how long we'll keep an empty instance around. If you have a lot of jitter in your workloads during the day, you might want to keep them around for 2 or 3 minutes to make sure that another workload doesn't need them. If you're in dev or staging, you might want to delete them immediately rather than just leave them kind of hanging around. Evictor is going to be our bin packer. So the evictor is what's going to look at every node in the cluster and start running real-time simulations and say, what's going to happen if I delete this node? It's actually going to take the pods that are on that node, run it through the real Kubernetes open source scheduler code, and ask the question, what would happen to these pods if this node went away? And we can actually simulate that. We can see where the pods would land, if they would get scheduled, if they would remain unschedulable. if they would all get scheduled on the remaining workloads, on the remaining nodes in the cluster, we're going to go ahead and cordon that node. We're going to do a graceful drain on it. We're going to let those workloads realign on other nodes in the cluster. Then we're going to delete it. We also have the aggressive mode. Aggressive mode sounds scarier than it is. It just allows us to ignore single replicas. So we can't tell whether or not a single replica is mission critical, right? That's up to our customers. Because it's a single replica, if it goes down or if it moves and there's a time where it's unavailable, some single replicas are directly customer impacting. Other single replicas are just a behind the scenes activity, something that's happening in the background, might be processing some batch, might be, annotating something, and it's not critical. Because we can't tell the difference between those, because we don't have access inside of the containers by design, this is up for customers to decide how aggressive they want to be. Go ahead and turn that on. So at this point, this is all the settings that you pretty much need. Now, there are a lot of other options you can do. For instance, you can create additional node templates. Node templates are sort of an analog to node groups. They're a lot looser defined, and they are useful for segregating workloads when needed. For instance, we recommend segregating your stateful workloads. It might not necessarily just be stateful sets either. It could be you've got a big monolithic Java Spring Boot application. It takes 15 minutes to start up. Maybe you don't want that sitting in with your Golang microservices that can come up and come online in 20 seconds. So you can lump those stateful things in together in a node template, isolate them, and keep them from getting moved around very often. Then you can have your default node group maybe be on spot instances, your default node template be on spot instances. That's where you can put all your microservices, everything that can move around gracefully, and really be able to tune that in. Another option is being able to have a GPU workload. So having a GPU node template. We have a lot of customers that do heavy ML training and ML inference using Cast AI. Because GPUs are so expensive, being able to have them just when you need them and then immediately scale them down when you don't is something Cast AI is very good at. We've saved a lot of our customers who are doing heavy ML training workloads upwards of 40% on their GPU usage. With how expensive GPUs are, those are big, big dollar items. Lastly, in the node configuration section here, this is where you can kind of dial in your nitty gritty, right? For those of you familiar with AWS terminology, this would be like your launch templates. So you can adjust your subnets, your security groups, your instance profile ARN, any of the settings that you need to do on the instance types. You can change which volumes you need. This is where you can really dial in the details. Most people don't need to change any of these things, but if you do, we wanted to make sure it was available. That's why it's not hidden, but it's a little bit less forefront, because most of the time these are all picked up as defaults and they work just fine from the defaults that are picked up from the cluster. I'm going to go ahead and do what we call a rebalance. So a rebalance is going to take the cluster that we have today, the 7 M5 large nodes. It's going to look at all the pods across those nodes, and it's going to reimagine the cluster. It's going to run a full simulation of what's the most cost advantageous cluster design, cluster shape that this could make. We generate the plan. Usually takes about 30 seconds. Here we go. So in this case, we can go from our 7 M5 larges to 4 different instance types here. They're all in the C family, different shapes and sizes. They're all pretty close in the CPU cost per hour. That's going to get us down to $212.65. We'll go ahead and let that run. So what that's going to do is it's going to create our new nodes first. So we'll see our 4 new nodes coming online momentarily. Okay, here's our 4 new nodes. So those are going to come up. They're going to become ready and join the cluster. Once they're ready, we'll start draining off the old nodes and migrating the workloads across. So we'll let that run in the background while we talk about some other things. But while that's running, I want to touch on workload autoscaler. This is something that we launched, I think it was about 9 months ago now. This is the next level of optimization. This is actually the much harder level of optimization. The reason it's so hard is it's because if you've got a central platform engineering team, that means you might have 6 people on your platform engineering team running all your Kubernetes infrastructure. You might have 30 or 40 development teams that are using those platforms. Each of those development teams gets to decide what requests and limits that they want on their workloads. 95% of the time, those requests and limits are significantly too high, sometimes by as much as 90%, particularly in dev and staging. A lot of times people only tune for production. So when they back that back down, they just use the same settings in dev and staging that they do in production, but they might have their HPA set differently. They might not have as many replicas in the lower environments. That's still a tremendous amount of waste. If we're looking at the actual environment in development, most of the time that's just sitting there idle, allowing things to be integration tested. Okay, let's bring up the browser. Let's make sure that everything loads. I just launched a new feature. I want to go make sure that it's working properly. That's dev, right? This is similar to my demo cluster here. These workloads, for instance, cart service. This is asking for 200 millicore. It only needs about 25 millicore from the actual runtime data. What this is doing is it's actually calculating the usage based on metric server and looking at how much CPU and memory are actually being consumed. What it's going to do is it's going to train on this data over a couple of days, watch the seasonality of the applications. You can tune in what percentile you want these workloads to be at. By default, we're at 80th percentile for CPU and 100 percentile plus a 10% overhead on memory. The reason we're so generous on memory is because kills are very dangerous. Kills are kind of one of the biggest problems that I run into in Kubernetes. Because memory is non-compressible, if your requests are too low, if you don't have guaranteed quality of service on the memory side of things, you'll go above your requested space and you'll go into kind of this burstable space between the request and the limit. This is also why we recommend requests and limits be set the same or very close to each other. As soon as you go above your requests, that's best effort space. That's fine on the CPU side because CPU slicing can be just fine. You can compress CPU and everything just gets a little slower. On the memory side, as soon as you run out of actual available space and workloads start fighting over that free space, you'll start getting kills. As soon as you start getting kills, you'll get very unpredictable, unstable experiences, particularly if you're in prod, you don't want to see that. We've run into a lot of customers who they don't understand why they're having unstable issues in their production environment. Most of the time, it's because the requests on their memory are set improperly. So right now, we're still in the learning phase. We've got low confidence, so this isn't going to be applied yet. Once it gains confidence, which is about 24 to 48 hours, we'll be able to actually enable this. Now, there's a couple of settings here that I want to talk about. One is the immediate versus deferred. So immediate, as soon as the recommendation and the actual requests are 10% different, or whatever you set them to be, this is configurable, it will automatically roll the pods and apply the new recommendations. With deferred is going to actually wait until the next natural pod restart. So the next time it gets moved around in the cluster, maybe it's the next time you do a deployment. Deferred is extremely useful on things like Node.js apps or Java apps, where you have a huge CPU inrush at startup. A CPU inrush will completely mess up your percentile. And if you're constantly restarting it, you keep getting those spikes, you're still going to be over provisioned. With deferred, you're only going to swap in those new recommendations when there's a natural pod restart. It results in much better answers on the workload. Okay, it looks like our rebalance has succeeded. We take a look at our savings. We're now running at $212.65. Looks like we could maybe get a little closer. This might be the evictor might tighten things up a little bit, but not too bad. So now if we talk about cost monitoring, kind of the last pillar here and kind of the thing I've touched on the least is the cost monitoring section. Now we have cost monitoring that goes for both the cluster level. Most people are interested in workloads and namespaces. So if we take a look at the workload level, this is able to track the actual costs for each of the workloads in the cluster based on what their CPU and memory requirements are and which specific nodes they're running on. So if you have one team that, for instance, says that they can only run on NVMe disks, they have to have NVMe disks. Great. That's going to reflect in their total cost. That requirement for more expensive instances is going to be reflected on their workloads. If you've got other teams who are willing to run on, say, spot instances and are very flexible, they run ephemeral nodes, they're very microservice oriented, they're going to get that benefit in here because we're not just dividing up the total cluster cost by CPU and memory percentages. We're looking which specific nodes everything is running on. This is part of our base platform. This is part of the free tier, as Josh mentioned. Gives you a really good understanding of where everything is going, where all your funds are going. Now, this is also API accessible. Everything we're talking about today is entirely driven through a Swagger API. Very easy to code against. If you want to pull this data out, a lot of our customers will pull this out and put it into, say, Power BI and be able to analyze that data to understand where things are going, track down which teams are costing the most money, and actually dig in to be able to fix that. Next is network cost. I apologize, I don't have a lot of data here, but network cost is going to be able to track which different pods are talking to each other and where those network traffic costs are coming from. For instance, our front end pod here has the most cross AZ egress, right? If you look at the details here, here are the different destination workloads. You can see load generator is by far the largest offender here, but then it's distributing work to all the rest of these. So now you can see which pods you might want to align on the same AZ to be able to avoid those cross AZ egress costs. You can dig into exactly what traffic is going where. Obviously, our load generator is talking directly to the front end, and so that's where this large amount of traffic is coming from. Now, if we align load generate on the same AZ as the front end, we would be able to eliminate those cross AZ egress costs. This is really helpful because this is one of the least understood areas of cost in Kubernetes and in the cloud. People see these ancillary EC2 line items on their bill. They're really hard to pin down to exactly what is causing those costs. So the network cost is very important. This is actually something that we're going to be starting to automate probably in Q3, where CastAI will automatically be able to migrate workloads that talk the most onto the same AZ next to each other if you choose to. That's going to allow us to automatically reduce these cross AZ egress costs without putting it back on the engineering teams. Lastly is the efficiency piece. So this is actually tied to our workload autoscaler, but you can see where the cost of those inefficiencies is coming in. So you can see how much it's costing you to be inefficient, which workloads are costing you the most. To our point earlier, when you have those 30, 40, 50 engineering teams that are all deciding their own requests and limits, using something like workload autoscaler, this puts the control back in the DevOps engineering team or the SRE team or the platform engineering team, particularly in those lower environments where you're a little less worried about causing any instability issues. The platform engineering team can now automatically threshold those workloads. So you can go in and say, I'm going to enable this. I'm going to enable it here. I don't think it'll take effect yet because we don't have confidence, but platform engineering can come in and enable this and say, yep, we're going to reduce your usage. You're not using it. We've tracked it over time. We're going to go ahead and throttle that back down. So this puts the control in platform engineering's hands. Now you don't have to go track down those 30 or 40 different teams with a spreadsheet and a bunch of TPMs and yell at them to reduce their cost. You just take ownership of it, take control of it. Maybe you don't want to do that in prod. There's too many variables. You don't want to accidentally cause downtime. That's fine. But in dev, it puts the control in your hands. Staging environment, QA, any of those lower environments, we've seen tremendous savings by stacking spot instances, workload right sizing, and instance right sizing to the tune of upwards of 90% sometimes. I've seen a development cluster that was $25,000 a month get throttled down to $1,500 a month. It was a 96% savings. And it took the customer about 3 days to do that. Amazing, amazing savings. And that's what automation, that's the power of automation. When you're trying to do this stuff by hand, you literally need to go in here every week, try to tune things by hand, make small adjustments, and it's very tedious, it's very toilsome. Last thing I want to touch on real quick here is the allocation groups. This is something that a lot of people have a really hard time wrapping their head around and being able to get a good picture of, particularly multi-cloud customers. If you're running workloads on GKE and AKS or GKE and EKS, it's very hard to see what your total costs are across those clouds. With allocation groups, you can actually create a grouping and you can span it across all of your clusters. So if you've got clusters in both, AWS and GCP, or if you just have 150 clusters in AWS and you want to see maybe what Datadog is costing you or what, New Relic is costing you, you can go in and select either the namespace or the label. So you can say, I want app equals ad service. So this is going to go in here and see what ad service is costing you across all of your clusters. So go ahead and save that. It's going to create our new allocation group. It'll take a few minutes for it to populate because it's going to start building that out now. But that's going to count all those costs across those different clusters. So this, for the FinOps folks, it's going to give them a really good picture of what everything it looks like across their entire fleet of instances. If you've got one workload that runs in every single cluster, now you can see what that's costing you in every cluster. That's incredibly hard to do by hand right now. Okay, I want to pause there. I haven't seen any questions come up in the chat. Does anybody have any questions that they want me to touch on? All right, I'm going to talk about our security functionality last, and then I'll hand it back over to Josh. So in security, this is kind of one of those areas that there's a lot of different passionate responses to it. Cast AI is working on having automated security, right? The goal of all of the Cast AI platform is automation. So in this case, we have a dashboard that's kind of looking across all of your clusters. We analyze for CIS benchmarks, best practices. We break it down by what exactly you need. You can look at whether they're a CIS benchmark, whether it's AKS, EKS, or just a Cast AI recommended. On image security, most customers have something around image security. There's various levels of accuracy out there. We've done a lot of work. We've brought in several both third-party open source and third-party paid platforms to pull together our vulnerability scanning or image security platform. So you can drill into what specific issues I might have. So in this case, we've got some CVEs in here. I'm running a relatively old code. This is a microservice that GCP launched a long time ago. And so we've got some good, examples of vulnerabilities in here. This one was from 12 months ago. You can see exactly what the issue is. You can see where the patch version is, or you could say, look, this isn't something that I'm going to be able to do with. I'm going to accept this as a risk. I'm going to take it off my plate. You can see which layers various things are coming in. You can also see which affected resources you have. Now, attack paths is a very interesting one. This allows you to actually visualize how an attacker would get to some of the vulnerabilities. So for instance, front end has access to the internet. So that's where the door is going to come in. So you can see which components are causing these vulnerabilities to be accessible from the internet. It gives you a really good visual, and you can track it right down to exactly what's causing it. And you can see what priority those issues are. If we get back to our automation, NodeOS updates. This is something that most people are not real good about. Leaving nodes around for several months, a lot of times that means that they're going to be running an outdated version of the NodeOS. So you're going to be accumulating vulnerabilities in, say, Ubuntu 2204 or Amazon Linux 2. Most of these are fairly new. These two instances are pretty old. With NodeOS updates, you can automate the rollout of patching your nodes. So you can set a schedule. You could set it to update on whatever cadence that you wanted to schedule on. So for instance, every night at midnight, I want you to roll nodes that are older than, say, 7 days. I don't care if they're spot or on demand. I want it to be done gracefully, but I don't want it to be any more than 5 nodes at a time. I don't want it to be every day at midnight. And you can save it. What this is going to do is every night at midnight, it's going to look for 5 nodes that are 7 days old or older, and it's going to do what we just showed, a rebalance, a graceful rebalance. It's going to create new nodes with the newest OS image. Then it's going to drain down the old nodes and gracefully migrate the workloads across. This is going to make sure that all of your nodes are patched and up to date constantly. Okay, that's kind of the last thing I wanted to touch on for security. Go ahead. Terraform. Great question. So through Terraform, we get the question a lot. Do we negatively impact Terraform? Do we cause state drift? And I'll actually expand on that to Argo CD as well. We get a lot of questions about, do we negatively impact Argo CD with the workload optimization? The answer is no, right? Because Terraform doesn't control the actual end nodes in the cluster. Terraform controls the node groups or the node pools. So it's controlling kind of the container that nodes are held within. We don't change those. The only cases you might need to change your minimum number of nodes in a node group or a node pool to 0, because if all of the nodes have been migrated to Cast AI, there might not be any nodes left in there. So that's the only thing that you may need to change in Terraform, is changing that to 0. Everything I've showed you today can be configured in Terraform. We have our own Terraform provider. We actually worked with HashiCorp not too long ago, and we are one of the most used Terraform providers across their entire fleet outside of the major cloud providers and the major enterprise kind of Terraform users. So we are one of the largest AI Terraform providers in their platform. For Argo CD and Flux CD, the reason we don't impact their sync issues is that we're not actually changing the version controlled item. So the version controlled item is the deployment. We're not changing the deployment. We're changing the pods. So your deployment stays in sync with your upstream, and we're only changing the downstream. So Cast AI is a direct replacement for Carpenter. So Carpenter, great tool. It's a point solution. It only solves a small slice of the problem. If you're using Carpenter today, Cast AI would be basically a direct drop-in in place of Carpenter. And we're typically seeing between 30 and 40% savings above and beyond what Carpenter is bringing. Carpenter's great. It's a good step in the right direction, but it still leaves a lot to be desired, and it also requires a lot of management. It requires a lot of hand-holding. I mean, we've talked to customers where they spent 6 months trying to tune Carpenter and getting it working correctly, and eventually they kind of gave up on it because it was just too problematic. I've worked with a lot of open source projects in my life. There's always a bit of tinkering that needs to be done there, so it's there's just a lot of time there. Cast AI is a lot easier. Like, we have a lot less settings. It's just a lot easier to implement. You also have, somebody else to yell at if things aren't working right. So we don't actually do recommendations. We do automation. So we'll tell you what the plan is. So if we go look back over here, if I look at my savings chart here, sorry, you see the before and after. And while these are sort of recommendations, we don't expect people to come in here and actually do these by hand. And Terraform is setting up the automation. It's putting the guardrails in place. It's putting the policies in place for the automation. But Terraform is not actually executing the changes. The changes are being executed by the platform, by the automation, by the engine. And that's the big differentiator between us and a lot of the other reporting tools that are out there. The reporting tools out there, they're great, but they're just creating more work. Right? They're creating a lot more significant effort on the engineering team's side, versus Cast AI is actually doing the work for you. So Cast AI is making the changes. So in this case, it looks like we had actually over-provisioned a little bit on that rebalance. It went through and adjusted it. That actually might be because I turned on workload autoscaler too. So we went from 4 nodes back down to 2. So we saved an extra $60 a month or so, and that's the automation. I didn't have to go in and run a Terraform anywhere. I didn't have to do anything like that. That was completely the automation taking care of that. If there's no other questions, I'm going to hand it back over to Josh.
Thank you, Phil.
Yep.
So I'm going to finish with a slide that I don't want you to judge because I created it rather than the marketing team. But ultimately, as I said, we find that DevOps gets caught in the middle with some of these organizational challenges. And it's certainly, we've had a number of customers who have, yes, it paid for itself. Yes, it saved money, but the sheer ability to get control of this environment from a DevOps perspective has gone a long way for them. And I will finish here and just leave you with a QR code you can scan if you'd like to book a demo or have a conversation with anybody on my team. Please do so. Other than that, thanks so much to everybody for joining us today. Hope you enjoyed the session and got something out of it.